All right. I see we have a few people already. Maybe we'll get a few more in the next few minutes. So let's talk about the exam that's coming up tomorrow. I just finished writing it, so that's good news for me, I guess. All right. So I think the exam will be assigned tomorrow, and it'll be due a week from a week from this Wednesday. So it'll be assigned on the 15th, and it'll be due sometime on the 22nd. All right. This PDF is not particularly online, but it is just homework 6. I just kind of added space to it. All right, let's begin. So, let's talk about the inclusion-exclusion principle just a little bit. So here, we have a whole bunch of stuff, right? So we have let's see. The number of things in A is 32, B is 34, C is 33, 15, 10, and 9. And so what we want to do here is we want to create a little Venn diagram. And so what we want to do is calculate the number of things that are in A intersection B intersection C, given that A union B union C is 72. So we have to use the double union formula, which says that the number of things in A union B union C is equal to the number of things in A plus the number of things in B plus the number of things in C minus the number of things in A intersection B minus the number of things in A intersection C minus again the number of things in B intersection C plus the number of things in A intersection B intersection C, like this. Okay, so let's fill in all the things we know. We know on this side 72 is equal to 32 plus 34 plus 33 minus 15 minus 10 minus 9 plus x, which is the answer that we're looking for. So let's see what all of this gives us. I think I constructed this problem correctly, but I guess we'll have to see. Okay. So this basically says that 72 is going to be equal to 65 plus x. And so when we finally do the arithmetic here, 72 minus 65 is 7. So yeah, this review is homework 6. I've just kind of respaced it out so that it's in landscape now, basically. Okay, so when we draw a Venn diagram of the situation, what we want to do is we want to put the middle one in first. So we want to put it 7 in the center. And then, for instance, now we want to subtract off all of these different intersections here. So we want to say 9 minus 7 is 2. For A intersection C, we're going to get 10 minus 7, which is 3. And here we'll get 15 minus 7, which is 8. So for the individual sets, it's a little more complex because you have to add them all up. So you have to say 8 plus 7 plus 3, that's 15 plus 3, which is 18. And so if we do 32 minus 18, we get 14. And so then if we do 34, 34 minus, 17 will be 17. And finally, 12. So what do we have? We have 33 minus 12, which is 21. And actually, we don't know what's out here because I don't give any information about that. So does this review lecture cover everything that's going to be on the exam? The answer is not really, no. I'm just going to cover homework 6 probably. That's probably all I'm going to have time to do. Basically, the exam is going to cover, the exam covers like homework 5 and 6. Okay, so this is the Venn diagram of the situation. How many elements are in exactly 2 sets? So what you do is the number of elements in exactly 2 sets. So really I shouldn't say this. It's 2 of A, B, or C, right? So it's either you're in A and B, or you're in A and C, or you're in B and C. And in those cases, if you're in exactly 2 of them, then that means that you're either this one, or you're this one, or you're this one. So it's going to be 2 plus 8 plus 3. Yes, that's 8 and 7. Okay, and then how many elements are in exactly 1 set, 1 of A, B, C? And so the answer to this one is, well, you would add up 14. Okay. I think I'm back. Yep, okay. I saw the stream glitch out for a second. All right, so let's go on to the next problem. Let me refresh the window here, because as it turns out now I can't see chat. All right. Cool. All right. So, so here's a really annoying question. But it's not so, well, it is bad actually. The good news is it's only 1 step. If you have 5 variables and you want to add them up to 63, so how many integer solutions are there? Remember, this is the stars and bars. So remember, it's the, if we call this n, it's n plus the number of variables minus 1. Choose the number of variables minus 1. And so in this case, we know that x1 is bigger than 0, so that's okay. x2, I guess. Or which one have I not done? Oh, let's just eliminate this one then. I mean, I guess technically, if I was being really stupid about it, I could say that both of these could be true, but let's just take the more restrictive condition. So if x1 has to be bigger than 3, then we have to create a y1, which is equal to x1 minus 3. And then what we'll do is subtract off a 3 from both sides, or 3 here, and we'll take n minus 3. And x2 is bigger than or equal to 0, so that's okay. We can leave that as is. For y3, for x3 we have to create a y3, which is x3 minus 4. And then we'll subtract off 4 from both sides. So minus 4 over here, minus 4 over here. For here, we'll create a y4, which is equal to x4 minus 1. And the last one will create a y5, which is equal to x5 minus 3. All right. So, and as it turns out, we can leave x2 as is. So we're going to create a new equation. The new equation is going to be 63 minus 3 minus 4 minus 1 minus another 3 on this side. Or not less than or equal to, just equal to. Is equal to, in this case, it's going to be y1 plus x2, which I didn't change, plus y3 plus y4 plus y5. And so the question is, what's going on over here? So this is 63 minus 3, which is 60, minus another 8, which is 52. So here we have 5 variables is equal to 52. So if the question is how many possible solutions are there, we're going to get 52 plus 5 minus 1. Choose 5 minus 1. So in this case, it's going to be, I guess it's 56, choose 4. I don't think I'm going to really evaluate this, and on your exam, you don't have to evaluate. So you don't have to evaluate these combinatorial terms. All right. Cool. Any questions or comments about this problem? I think you guys have seen this problem before, so shouldn't be terribly surprising. Yeah, so the 52 came from this big circle here. So what happens is, remember that every time we create these new variables, we have to subtract off, for instance, 63 minus 3 for the x1. For x3, we have to subtract off 4. For x4, we have to subtract off 1. And from x5, we have to subtract off 3. So that's what we're doing there. And then we realize that actually our equation is not equal to all of these things equals 63. It's actually, if we subtract off these values, it's actually all these things equals 52. Okay. So let's go on to the next one. I think the next one is more complicated. Yes, it is. So calculate the number of solutions without the 2 upper bounds. So basically, you notice that I made this problem relatively simple. There's no problems with the lower bounds. They're all just 0. So if we ignore the upper bounds here, well, basically in this case, y2 is equal to x2. Because, it's technically minus 0. Yes, it's n plus the number of variables minus 1. Choose the number of variables minus 1. It's actually, basically you could call it stars plus bars minus 1. Choose bars minus 1. All right, so let's go back to this problem. So now we're dealing with x1 plus x2 plus x3 is equal to 22. And so what part A says is just ignore these upper bounds. So I've crossed them out for now. The upper bounds don't really exist. So in this case, we're free to do whatever we want. We can just say it's 22 plus 3 minus 1. Choose 3 minus 1. And we're good. right? That's equal to 24, choose 2. And that's fine. So there's not a whole lot to do here. But now, let's say that we want to calculate the number of solutions where x1 is bigger than 5, but 0 is still bigger than... So what we're going to do is we're going to say x1, if x1 is bigger than 5, that means that x1 is bigger than or equal to 6. So if that's the case, then we have x1 plus x2 plus x3 is equal to 22. And if I subtract off 6 from both sides, and then I call x1 minus 6, right? We'll call that equal to, say, z1. Then z1 plus x2 plus x3 is equal to 16. And so because of that, we can write down the answer again. We know that the sum is going to be 16 plus the number of variables, which is 3 minus 1. Choose 3 minus 1. Cool. So as it turns out, the whole thing here, this is just 18. I keep hitting a button. All right, so let's do it again. So now we're going to calculate the number where x1 is bigger than or equal to 0. So that's just as regular. But x2 has to be bigger than 4. And so what does that mean? And let me eventually erase these upper bounds. So what that means is that if x2 has to be bigger than or equal to 5, so let's do it again. So what we're going to do is we're going to say, okay, here we have the equation, x1 plus x2 plus x3 is equal to 22. And we're going to subtract off 5 from both sides. So now x1 plus, say, k2 plus x3, and we can even just call it x2 with a bar over it or something, where x2 bar is equal to x2 minus 5. And so instead of 16, this will be 17. And so what we can do here is we can say, well, this is 17 plus 3 minus 1. Choose 3 minus 1, which is the same thing as saying, well, maybe I should not write the 1 into the... There we go. Which is the same thing. Whoa. Okay. Let's try that again. Okay. I am not sure why it's doing that. Seems to be having a little bit of a spaz out. Okay. All right, good. Hopefully it doesn't do that again for whatever reason. Okay, so let's see. 17 plus 3 minus 1, that's 19. Choose 2. Okay. Cool. But we haven't solved the original problem yet. So now we have to do 2 more things. So now we have to calculate the number of solutions where x1 is bigger than or equal to 5 and x2 is bigger than or equal to 6. Or I'm sorry, x1 is bigger than 5 and x2 is bigger than 6. Is that bigger than or just bigger than or equal to? Oh. There we go. So in that case, we're going to get x1 plus x2 plus x3 is equal to 22. And so in this case, what we're going to do is we're going to subtract off 5 from both, 5 and then 6. So then we're going to have x1 bar is equal to x1 minus 5. We're going to have x2 bar equals x2 minus 6. So actually we're subtracting off 11 from this side. So what we're going to get at is x1 bar plus x2 bar plus x3 is equal to 11. And so we can do the same thing again. So in this case, it's going to be 11 plus 3 minus 1. Choose 3 minus 1. So in this case, it'll be 13, choose 2. All right. So now we want to calculate the final answer using the inclusion-exclusion principle. So what we have to understand is, like, what have we been doing these past 10 minutes or 5 minutes or whatever? We've been reusing the same formula over and over and over, but what have we been doing? If we say that, let's think about it. So we want the solutions to all of with all of these constraints. And so let's call A the fact that x1 is bigger than 5, and B is the fact that x2 is bigger than, this is bigger than, yes, bigger than 5, bigger than 4. There we go. So so the thing about this is that if we have those two events, then what we know is that the total number of solutions is equal to the number of solutions where we're considering basically all the solutions without either constraints. So how should I say this? I guess we'll just draw a Venn diagram. So here's all the solutions. And we want the solutions where 0 is less than or equal to x1 is less than or equal to 5, and 0 is less than or equal to x2 is less than or equal to 4. And so what we've computed is the number of solutions where basically we want, so if this is the set where all the solutions are bigger than 5, or A is the set of solutions where 0 is less than or equal to x1 is less than or equal to 5, and this is the set of solutions where 0 is less than or equal to x2 is less than or equal to 4, then we want this intersection. We want to know how many things are in the intersection. So in order to compute that, what we're doing is we're saying, let's take all the solutions from this whole set here, and what we know is that basically if we add up the number of things in the universe and then we subtract off the number of things in A, subtract off the number of things in B, and then add on, I guess we could really say it this way, the number of things in A union B minus this, plus the number of things in the intersection. Now, of course, this is what we want here. This is equal to the total number of solutions, where both of these, or I should say, yeah, so this is equal to the total number of solutions. And so, how are we going to do this? So what we're going to do is we're going to look at it like this. The total number of solutions here is 24, choose 2. And then we're going to have to subtract off we're going to have to subtract off the number of things in this set here, which is 18, choose 2. And then we'll have to subtract off the number of things in the other set, which was, if you remember, it was 19, choose 2. That's good, I checked. 19, choose 2. And then we add on the things that are in the last set, which is 13, choose 2. And so this is the number of solutions. So as it turns out, this is kind of a hard problem because there's not really, as far as I'm aware, a simpler and better way to kind of attack it. You kind of have to do each one of these things individually, and then you have to just use the inclusion-exclusion principle to deal with it. All right. So part D is the double intersection, or it's the thing that we're going to add on in the end. So you notice that this part here went in here. Okay, so let's look at let's actually just move on and do this problem. Let's see. Why is part D x2 is bigger than 6 and not x2 is bigger than 4? Oh, good question. I think, was this a typo that I just did not fix? It looks like it is. So yes, this needs to be 4 and not 6. So this needs to be 13 and not 11. And so this needs to be 15, 15. Yeah, so in terms of the exam format, you will be sent a PDF. You will have 1 week to complete the exam. That's it. There will not be... Oh, yes, so let's make this 9, 13. Okay, so there is no restriction in terms of, like, you can use books, you can use notes, you can use lectures, you can... The only thing I ask is that you not actually work together on that. But yeah, other than that, you can use any resource from the class that you can find. Okay, so let's move on to this. Okay, so, right. Let's look at this thing. Oh, crap, I didn't actually look, no space here. No space. I was a little confused. I was like, I had A and I had B, but then I have C and D. I was totally confused. I did not understand what was happening. Yes, so given probability of A is 0.3 and probability of B is 0.6, probability of A complement intersection B complement is 0.7. Then what is the so I'm going to do this problem here. Actually, I'll do it here. So what we do, the first thing we have to do is remember what the probability... Well, okay, so the first thing we have to do is ignore the word probability, and we just have to ask ourselves, what is A complement intersection B complement? And so a lot of you, as soon as you see me writing it out, are going to think to yourself, ah, crap, that's the that guy again. It's like the only thing that I taught in the first few weeks of class, right? So, De Morgan's law. Okay. So what this means is that if this is true, then the probability of A union B is going to be 1 minus 0.7, because this is A union B complemented, so it's everything outside of A union B. So if this is A, this is B, then this is A union B complement. And so A union B is impossible, right? 0.3. Did I mean to do it the other way? What did I do in this problem? We're Or did I just flip numbers, or what the heck did I do? I mean, so as stated, this problem is impossible because 0.3 is going to be equal to 0.3 plus 0.6 minus x, and then, you know, we're going to end up with so x is going to be 60%. The problem with that is that it's bigger than the set A. What must I have meant by this? This seems like a weird screw up even for me. Well, I mean, okay, fine. I must have just not been making sense. So let's change this problem so that it makes sense. Because otherwise it just is garbage. So what number do we have to change this to make it work in any sense? Oh, I was probably just thinking that the union was equal to 0.7, so maybe the intersection should be 0.3. Does that work? It probably does. So let's do everything the same, except just consider this to be 0.3. So now we have the probability of A union B is 0.7 and not 0.3 anymore. And so if that's the case, then we'll actually get something kind of more meaningful, because we can say 0.7 is equal to 0.3 plus 0.6 minus x. 0.7 is equal to 0.9 minus x. And so as it turns out, A intersection B probability, I must have changed this. I must have written this as the union and then changed this later on and not fixed it. I mean, almost certainly that's what I did, because this makes sense. But that, as stated, did not make sense. So I think I must have just thought that I had fixed it. Okay, hopefully this problem makes more sense. So this problem is a little bit interesting, I guess. So basically here, and I think I was a little more careful when I made this, so hopefully it's right. So we have the probability of C is 40%, the probability of D intersection C complement is 30%, and the probability of D is 50%. So let's look at how the Venn diagram works for this. So the Venn diagram here, the probability of C, but the probability of this thing plus this thing is 0.4. So we don't know what the probability of specifically this block or this blob is. We know that the sum of these two is 0.4. This one, let's look at the, okay, so this is saying the probability of D is 1/2, and then what is this thing telling us? The probability of D intersection C complement. So it's the part of D that does not include C. So it's actually this part. So given that fact, we know that this part here is 0.3, and we know this total thing is 0.5 because I set it here. So this intersection here is going to be 0.2. And so if this intersection is 0.2, then the part that's just in C is 0.2. And so if we add these things up, then we get 0.2, 0.2, 0.3. We add them up, we're going to get 0.7. So the C union D is 0.7. C intersection D is 0.2. And if we cared, there's 30% stuff outside. It didn't ask for it, but what's the probability of C union D complement? So that's also a valid question that we could ask. Okay. So let's look at the next problem. Oh, this is a fun one. So there's two ways to do it. Oh, I'm drawing by accidentally touching the thing. Okay. So there's two ways to do this problem. There's the boring way, and there's the fun way. So let's do it the boring way first. This is how I used to teach journalism majors to do it, so this is the easy way to do it, but it's also boring. What we're going to do is we're going to list out all the possibilities of two dice rolls. So 1, 2, 3, 4, 5, 6. There we go. 1, 2, 3, 4, 5, 6. And so we're looking for the sum to be 8. So if we have two dice, we want x plus y to be equal to 8. And so you say to yourself, oh God, I know how to do this. But don't jump the shark yet. Because what we're going to do here is we're going to say if this is x and this is y, then we can write down all the possibilities. The x plus y here is 2. 2 plus 1 is 3. 3 plus 1 is 4. So we're adding 1. Here we're going to do 2 plus 1, which is 3. 2 plus 2, which is 4. 2 plus 3, 5. 2 plus 4, 6, 7, and 8. Then we're going to do 3 and 1, which is 4, 5, 6, 7, 8, 9. 4, so we're going to get 5, 6, 7, 8, 9, 10. 5, so we're going to get 6, 7, 8, 9, 10, 11. And 6, so we're going to get 7, 8, 9, 10, 11, 12. So there's a few things that we see when we look at this. The first thing that we see is that all the diagonals, so here's a diagonal, here's a diagonal, here's a diagonal, here's a diagonal, etc. They're all constant, as it turns out. Okay? All the diagonals are constant. So if I ask you how many times, what's the probability that a sum of 8 occurs? Well, how many total possibilities are there? As it turns out, well, the total number of possibilities, right, the number of things that occur is equal to 36, because it's just 6 times 6. So then we can count up the number of ways we see an 8 happen. 8 happens here, 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 here. So the total answer is 5 out of 36. So here's the question. Was that boring? Maybe it wasn't, since I haven't actually shown this in class before, but I mean, I think it's boring because I've seen it so much. So yeah, it wasn't actually that bad. It wasn't that bad. Everybody, all the journalism majors complained, if you know what I mean. None of them liked it. But here's the fun way. We have two equations, or we have a single equation. We have two sets of constraints. So as it turns out, oh, and one thing to say about this chart. A lot of people say to themselves, oh, well, a 3 and a 1 is the same thing as a 1 and a 3, right? A 6 and a 4 is the same thing as a 4 and a 6, right? So should we be considering both of them as the same thing, or should we, right, should it actually be out of 18 instead of out of 36, and we should ignore the lower half of this table? Some people ask that question, and the answer is, in this case, no. We do not want to ignore the lower half of this table for this reason exactly, because there are two ways to roll a 1 and a 5, right? You can either get a 1 and a 5, or you can get a 5 and a 1. Now, you might say, well, I don't care. I can just rearrange them, and then they're the same thing. But the difference is that if you got a 3 and a 3, for instance, if you rolled a 3, and then you roll another 3, 36 is just 6 times 6, right? There's 6 options for a single die, and there's 6 options for this one. And so the distinction here is that if you rolled a 3, and then you roll another 3, as it turns out, that is truly one possibility, right? Whereas these things are actually technically two possibilities. Or if you consider them to be one possibility, then you have to keep in mind then the probability of that one possibility. If you say that it's the same to get a 5 and a 1 as a 1 and a 5, you have to say that the probability of that is twice the probability. Here, when we look at this chart, all events are, all outcomes are equal. So if we distinguish between a 1 and a 5 and a 5 and a 1, then all outcomes are equal. If we say that 1 and 5 is the same thing as a 5 and a 1, then we have to distinguish between where x is equal to y and where x is not equal to y, and there's different probabilities for different outcomes. Here, we can just literally add up and get 5 out of 36. There, what you would have to do is, if you're only paying attention to the top half of this table, what you would have to do is you'd have to say this gets a 1, this gets a 1, but this is 4 and 4, so it gets a 2. So I would add up right? Oh, I'm sorry. Other way around. This is a 2, this is a 2, this is a 1. So, right, you would end up getting something like 2 plus 2 plus 1 over 36. If you did it that way, which is a little bit more complicated. Okay, so that was the middle way of doing it, which I actually never teach that way because I think it conflates everything in the chart. You'd have to remember that everything off the diagonal in the chart has twice the probability of the diagonal, and I don't know. It's probably just better to do everything with equal probability. So on the other hand, here's the fun way. So the fun way is basically we repeat the steps from the previous thing. So what we do is we say, okay, well, let's subtract off. So is this a permutation problem? Well, it's actually neither, because you can get duplicates. So if you're allowed to get duplicates, then it's not really either a permutation or a combination problem. I will tell you what it is in just a second. It's actually a strange version of a combination problem. Because it's actually a star and bar problem. And let me show you why. Let me just do the problem on a new page. So remember what I wrote on the previous page. I wrote x plus y is equal to 8, and I wrote 1 is less than or equal to x is less than or equal to 6, 1 less than or equal to y less than or equal to 6, and then you say, oh my god. This is the same thing as the previous problems that we were just doing with the inclusion-exclusion principle and the stars and bars stuff. So what we need to do is we need to compute all the possible solutions where 1 is less than or equal to x, 1 is less than or equal to y. And so if we do that, then we have to subtract 1 from each side, or I'm sorry, 1 from x, 1 from y, and 2. So we're going to get x bar plus y bar equals 6. So the number of solutions is 6 plus 2 minus 1. Choose 2 minus 1. So the number of total solutions here is just 7. Choose 1, which is also known as just 7. But then we have to compute the number of solutions where x is bigger than 6. So if x is bigger than 6, x is bigger than 6, so then we have to subtract off 7 from both sides. So we're going to get x plus y is equal to 8. And so we subtract off 7 from both sides. Whoops, not from here. There we go. And so in this case, what we're going to get is there's two possibilities. Either x is equal to 7 and y is equal to 1, or x is equal to 8 and y is equal to 0. So those are the two possibilities. So, and we're going to see that here anyway, because we're going to get an answer of 1. So we're going to get 1 plus 2 minus 1. So that'll be 2. Choose 1, which is 2 solutions. And then we see it's the same thing if we set y bigger than 6. So y is bigger than or equal to 7. And we do the same thing, except now we have x plus y is equal to 8. We subtract off 7 from both sides. Can you do both x bigger than 6 and y bigger than 6 in the same step? No, you have to do that last. So let me show you. So we're almost done with this step. So here you're going to get another 2 choose 1, which is equal to 2. And so let's see here. Interesting. So anyway, okay, so now what we're going to do is we're going to say x plus y is equal to 8, where x has to be bigger than 6 and y has to be bigger than 6. So now this is both. Well, if that's the case, then we have to subtract off, we actually have to subtract off 7 from both. And so how many solutions are there when we subtract off 14 from 8? So we're going to get minus 6. So we're going to get x plus y is equal to minus 6. And the rule is that x is bigger than 0 and y is bigger than or equal to 0. So you don't even need combinatorics to figure this one out. You can just say, well, a positive or a non-negative thing plus a non-negative thing is never equal to a negative thing. So there are 0 solutions. So, okay. Oh, because, I see what I've done wrong here. So we have to still subtract off 1 from this because we still have 1 is less than or equal to y here, and still we have 1 is less than or equal to x here. So we actually have to subtract off another 1. So as it turns out, we don't get this. We get 0 choose 1, which is 1, or actually 0 choose 1, which is 1. Here we get 0 choose 1, which is 1 again. So yeah, because we have to subtract off 1 because of the lower bound. So basically here, what we have to do now is, actually, it's not 0 choose 1, it's just 1 choose 1. let me be more careful about this. So yeah, it's going to be 0 plus 2 minus 1. Okay, that didn't write at all. Let's try again. And that is 1, choose 1. Okay, so what we end up getting here, and so now the total number of solutions is 7 minus 1 minus 1 plus 0 by the inclusion-exclusion principle. So the total number of solutions is going to be 5, and then we divide by the total, which is 36. So this is definitely the fun way to do this. I hadn't thought about the fact that it was definitely going to be longer, actually, and probably harder, and also more prone to error. Mainly because I got it wrong initially. I forgot about the lower bounds for x and y when I was doing these two parts. So I would suggest just sticking to the regular thing, but this is just an interesting side note. I think that this is a way better thing to do. Actually, what I could do after this lecture is I think now I actually have the ability to export these things as PDFs, so I could actually just send out what I've done so far. Okay. So let's talk about, so this is going to be the binomial distribution. And so you remember that the probability in the binomial distribution of k successes is n choose k, p to the k, q, which is really just, I'm just sticking to statistical notation, q to the n minus k. And so that is what it is. And so we can use this to calculate things. So if we ask what is the probability of at least 2 successes, then at least 2 in a set of 5 trials is x is equal to 2, 3, 4, and 5. So what we can do is we can just add up, for instance, 5 choose 2, 0.35 squared, and then we have to do 1 minus 0.35, which is equal to 0.65. Okay, that did not write very well. Okay, times 0.65 cubed plus 5 choose 3, 0.35 cubed, 0.65 squared, plus 5 choose 4, 0.35 to the first power, 0.65 to the fourth power. Wait, no, backwards. The fourth power to the first power. Plus 5 choose 5, 0.35 to the fifth power, and then technically there's a 0.65 to the 0, but that's just equal to 1. So that is how to calculate that. So let's talk about the probability of at least 1 success. And so you might be thinking, oh God, this is worse than the probability of at least 2 successes, except we're going to do it in the shorter way. So the shorter way to do it is to say, well, the probability of at least 1 success, which means 1, 2, 3, 4, or 5 successes, basically the secret is that it's not 0. So instead of doing it the direct way, we can actually just say, well, it's not, so we complement, right? It's not the probability that x is equal to 0 successes. And so what is the probability of 0 successes? Well, the probability of 0 successes is 5 choose 0, which is 1, times 0.35 to the 0 power. Now I have to erase this because and then we have 0.65 to the 5th power. So as it turns out, this is a very easy thing to compute because 5 choose 0 is 1. 0.35 to the 0 power is 1. And so the only thing we actually have to do is do 1 minus 0.65 to the 5th power. And so this is definitely a way shorter way to do this. Now you could say, oh, well, we could actually do the same thing up here and compute this one the same way. And the answer is yes, you can. Yes, so you can do 1 minus 0.65 to the 5th minus 5 choose 1, which is 5, times 0.35 times 0.65 to the 4th power. So that you can actually compute this thing this way. It just depends on which one is longer and which one is shorter. So what is the probability of no successes? Well, we already know that. We've just computed it. It's 0.65 to the 5th power. And so going back to C, between 2 and 4 successes, unfortunately, there's no great way to do this. Especially if I said some binomial probability that's like, you know, there's 800 trials. What's the probability of between 600 and 700 successes? You would just have to add up basically 101 different possibilities. Unfortunately, there's not a terribly great way to do this. Well, except for something that I haven't taught because it's, I think you'll learn it in Stat 355. So you'll learn the normal approximation to the binomial distribution. So I'm just copying from here, right? It's just this term plus this term plus this term. And there's really nothing complicated about what we're doing here, except that we have to do it a bunch of times. There we go. That should be good enough. So yeah, this is basically the binomial distribution, how to deal with it. Yeah, so there's nothing terribly complex about applying these formulas. As I say, it's just if you have to apply a ton of them, it'll end up getting kind of long and pretty tedious. There is actually a way of using the normal distribution. So if you guys know about the normal distribution, it's the bell curve. Is it the square root of 2 pi like that times e to the minus x squared over 2? I think that's the equation that defines the normal distribution. And probabilities on the normal distribution are integrals of this normal distribution function. So if you want to know, for instance, the probability that you land between, say, alpha and beta, it's the integral from alpha to beta of f of x dx. As it turns out, there's a way to convert between the binomial distribution and the normal distribution. But as I say, I think I am actually going to not teach that in this class, mainly because it's really a Stat 355 thing, and also the normal distribution is a continuous distribution, and if there's anything I know about this class, it's called discrete. One nice thing about the normal distribution is that it's an example of an integral that you can't actually do using standard methods. And I shouldn't just say by standard methods, I should say by essentially any method. There is no method that can actually do this integral except for approximations. So that's kind of an interesting fact about mathematics, is that this integral is not really computable in exact terms. You have to approximate. So here's a good little practice problem. So I never thought about it this way, but there's two ways to do this problem. So you want to show that k times n choose k is equal to n times n minus 1 choose k minus 1. So we can do that using the symbols. So n choose k is n factorial over k factorial n minus k factorial. And so we're going to multiply k by it. And so what I'm going to do here is I'm going to say to myself, all right, in this case, guess what should I say about this thing? Oh yeah, had a senior moment for a second. I forgot where I was. K factorial is equal to k times k minus 1 factorial. And so basically what we get to do here is we can kind of pretend to cancel like this, except if you're going to cancel like this, you can't cancel the whole thing. You're really canceling with that, so what we're going to have to do is multiply by k minus 1 factorial now. And then, unfortunately, what you have to do is you have to ask yourself, okay, then you ask yourself, what is n minus 1 factorial? Oh, I'm sorry. What is n minus 1 choose k minus 1, which is n minus 1 factorial, which is divided by k minus 1 factorial. And then here's the hard part. It's going to be n minus 1. And then, of course, here's the hard part where you have to remember to distribute minus k minus 1. If you forget these parentheses here, then what's going to end up happening, and then, of course, that has to be factorialed. If you forget those parentheses, you're going to end up with something that isn't correct. But here, if you notice that we have n minus 1 minus k, which is good, right? Because we want n minus k factorial. That's our goal. And so this minus and this minus join forces and give us, we're going to have n minus 1 minus k plus 1 in here. And that's nice because these will cancel. And so as it turns out, we have just proven, because this thing is n minus 1 factorial divided by k minus 1 factorial n minus k factorial. This is n factorial divided by this. Well, what is this missing? Right? This term is missing an n in the numerator. It's missing an n in the numerator, which we get from this thing right here, so we can add this on. So now are they equal? The answer is yes. I was just reading a textbook today while I was writing your exam that asked for a combinatorial argument to prove this fact. And I think that's very nice. The combinatorial argument that I'm coming up with, at least right now, is you choose k things out of n things, and then you pick an element that gets a star on it. So basically what you do is you pick k things out of n things in a bag, and then one of those things that you just picked gets starred. So you have k things that you picked, you have the n minus k things you didn't pick, and then you pick one of them and you put a star over one of them. And then over here, basically, if you have a bag with n things, you pick one thing and you put a star on it. So that's one thing that gets the star. And then out of the bag of n minus 1 things that are now left, you pick k minus 1 things. And then here's n minus k things. And so the question is this selection process equivalent? And the answer is yes, because this element that gets the star on it is distinguishable now from the other elements. So even though it's in the bag with the k elements, really, this element is now distinguishable because it has a star attached to it. So what you can do is you can now say that this is 1 and k minus 1 elements, and one of them has a star on it. So as it turns out, that would be the combinatorial argument that shows that the two things are equivalent. Okay, so let's write out the expected value formula for the binomial distribution. So the expected value formula for the binomial distribution is going to be the sum from k is equal to 0 to n of k times the probability that x is equal to k. So this is not just the expected value formula for the binomial distribution. This is the expected value formula, right? In general. The only reason why this is the expected value formula for the binomial distribution is because this is the binomial probability. So now we replace, whoa, that was one of the most disgusting summations ever seen. Slightly better. So here we're going to put a k times n choose k times p to the k times q to the n minus k. And so here what we're going to do is we're going to say n is equal, or k is equal to 0 to n. And this is the expected value formula for the binomial distribution. Now, of course, here I have to actually erase some of this stuff here so that you can see what we're going to eventually prove. We're going to prove that the expected value formula of the binomial distribution is NP. So how do we do this calculation? Well, it shouldn't shock us, right, that this fact is going to come into play, right? So if I didn't tell you this fact, if I didn't make you show this fact before, you might say to yourself, oh, good God, this is a massively, like, to a 203 student, to even me sometimes, this is complex, right? This is, and you look at it and you're like, oh God, there's 4 different things I have to worry about, and they're all kind of moving around because every time k changes, this changes, this changes, this changes, that changes. How on earth do I get a handle on this summation? Well, maybe if I replace k times n choose k with n times n minus 1 choose k minus 1, maybe something will shake out. So let's see what happens if we do that. So the question that I have is, why can't we factor out this k? Why can't this k come out of this summation? I keep hitting this stupid button. There we go. And nothing changes about p to the k, and nothing changes about q to the n minus k. So if the question is, why can't k pop out of the summation? At least in terms of computer scientists, we should basically say, well, k is the variable that our for loop, if a summation is a for loop, right, then k is the variable that the for loop declares, right? K is the for k in range, or for k int k is equal to 0, k less than whatever, k plus plus, right? So depending on what language you're doing, who cares? But the thing is that k is the variable that our for loop is iterating over. So that's why we can't take k outside of the for loop, because k doesn't really exist outside of the for loop, or k in this case doesn't exist outside of the summation. On the other hand, n has no such problems. N's completely fine, right? So n can move outside of the summation, and the reason why it can is because here the variable is k, and it goes up to n, but n is a fixed constant here, and so that's very nice. So, okay, that's good. And now the other thing I'm going to factor out, I'm going to make this k minus 1, and I'm going to pull out, so what that means is, remember that p to the k is going to be equal to p times p to the k minus 1. And so what we're going to do is we're going to factor out that extra p. And so remember that p is also factorable outside of the summation, because p is not being summed over either. It's just k. So once we have all of that, we have the expected value sitting right here, and we have this summation. And so if all things are just in the universe, right, justice plus hope means that this summation should be equal to 1, right? Because if this is the expected value formula, this is the way to compute it. We use this trick, and then we have this thing here. We need to say that this whole formula here, except without the NP, so the NP is the thing we want to keep, the rest of this garbage has to be equal to 1. Well, the question is why? Why is this equal to 1? So let's do this on a new page. We want to look at the summation of k is equal to 0 to n of n minus 1. Choose k minus 1, justice plus hope. I guess that's going to be my political slogan when I run for office. I guess the only problem is that if I don't live up to my word as a politician, people are going to write other equations. Like, oh yeah, Eric minus hope equals whatever, horrible things. So, yeah, doesn't look like I'm going to win the 2020 election. So anyway, so our goal is that this is equal to 1 here. So you say to yourself, well, okay, cool. There's one thing that we know about a probability. Well, there's actually 3 things that we know about a probability distribution. The one of those things that we know about a probability distribution, rule 1, is that the sum over all the outcomes of the probability that x is equal to that outcome is equal to 1, right? The outcomes sit inside of the sample space. And so what we know is that the sum of all the probabilities is equal to 1. So my claim here is that this is actually summing up all the probabilities, not from the binomial distribution on n elements, but this is the binomial distribution on n minus 1 elements. And so what is the probability of anything given that? So we can ask that question. We can basically say it's equal to, well, n minus 1, choose something, p to the something, q to the n minus 1 minus that something, right? So that's the probability that x is equal to something. And so in order to calculate this probability, what if I set k minus 1 equal to the something? Then we're going to get n minus 1, choose k minus 1, p to the k minus 1. And now here, we do the same trick that we did before, n minus 1 minus k minus 1, right? But if I don't write the parentheses in, this isn't going to work. But if I write the parentheses in correctly, then, oh, wait, this minus sign distributes again. We get n minus 1 minus k plus 1. And so that's why here we have a q to the n minus k, and there's no mention of plus or minus 1. That's why this thing is like that. So this is truly the binomial distribution on n minus 1 elements. The only little thing that you might care to say is that on the 0 term, we're going to end up with n minus 1. And so you're going to notice that it's not choose 0, it's choose negative 1 times p to the negative 1. So that's 1 over p, which is no good, q to the n minus k, which is going to be 0, so that'll just be n. So the question is, what the heck is this term? The answer is, remember that basically if you have a garbage term, if you have like n choose k, where n is less than 0, or k is less than 0, or some weird thing that's not really defined, just set that to be 0, right? So that helps us because otherwise we might actually have to deal with that term. So the good news is that it's usually tradition to set the garbage combinatorial terms. Like if I say, out of a bag of n things, pick negative 2 things, you would say, that doesn't make any sense, I'm not going to do it. And in that same sense, 5 choose negative 2. The number of ways to pick out of a bag of 5 things, negative 2 things, should be 0, right? So if it's not 0, then that's a problem. So that's cool, right? So now we've shown that this thing is truly just the binomial distribution on n minus 1 elements. So that means that we go back here and we put a big arrow through the whole thing and we just write that this is equal to 1. And we're done. So that means that the expected value of the binomial distribution is n times p. So what does that really mean? What that really means is that the expected number of things that will be successes is equal to, unsurprisingly, the number of trials times the probability of success. So yeah, that's really it. So if I roll a die 6 times, and a success is getting a single 1, then if I ask you what's the expected value of this thing, well, it would be the number of trials, right? 6 times the probability of getting 1, which is 1 over 6, which is 1. Now, of course, what that's saying is that we expect a single 1 on 6 trials, which totally makes sense. We're rolling a die 6 times. We want a 1 to pop out, and it does. So there we go. Okay, so we've just proven a fun fact about the binomial distribution. All right. Let's do this question. We can do this quick. So this is actually much easier than the previous question. So let's define a function on n where the probability of success is 1 over 2 to the n plus 1. It does this define a probability distribution. So the answer is going to be maybe. The real question, so we can always assume that the probability of the empty set is 0. So that's good. And so we also need that the probability of any outcome is between 0 and 1, which is definitely true because 1 over 2 to the n plus 1 is less than 1 most of the time, in fact all the time, and it's always bigger than 0. So that's true. This is true. I'm not going to verify condition 3, which is, if you remember, it's going to be the double union principle. We're just going to assume that the double union works. That leaves one thing left to verify. The last thing we have to verify is that the probability of the sample space, which is equal to the sum of all the outcomes, right? And we have to verify that this is equal to 1. And so the question is it equal to 1? And so let me just write this in a little bit better notation. This is n is equal to 0 to infinity of 1 over 2 to the n plus 1. So as it turns out that this is what's called a geometric series. And so any geometric series has a sum. So the sum of the geometric series, 1 over, well, let's just make it the geometric series on alpha. Is equal to 1 over 1 minus alpha. So as it turns out, there's only one small modification we have to make to this. We see that there's this extra plus 1 in here. So what I'm going to do is I'm going to rewrite this as 1/2 like that. Now, if you notice, the reason why I'm doing that is because if I don't do that, then we're going to get 1 over 1 minus alpha, and it's going to be off by just a factor of alpha, actually. So then we use the formula. So we say this is 1/2 times 1 over, can't get it to draw 1 minus 1/2. So in this case, 1 minus 1/2 is 1/2. 1 over 1/2 is 2. And I usually write this down. I guess I haven't had to do this yet in this class. A over B over C over D, right, is equal to AD over BC. I don't think I've ever actually written that in this class yet, but that's true. So in this case, 1 over 1/2 is 2. You can also say some stuff about reciprocals. I'm perfectly happy for you to say stuff about reciprocals. So this is 1/2 times 2, which is known finally as 1. And so it is definitely now true that this thing adds up to 1. So does it define a probability distribution? Yes. If I'd left off this plus 1, then it would have almost defined a probability distribution. The only thing that would have been a problem is that the sum of the sample space would have been 2 rather than 1. So that would have been a sum of 200% rather than 100%. So not a big problem. You can actually renormalize. But on the other hand, it's not exactly a probability distribution either, so that's why we needed the extra plus 1 in here. All right, so that's a fun, I like this problem. This is a fun problem. It's a fun problem because anytime you get to use the geometric series, you're having fun. All right, let's do the last problem. This is by far the most actual fun. This is not just mathematical fun. This is actual. Crap! Can't you write a T? U-A-L. So this is actual fun, and the reason why this is actual fun is because I wish this was a tree problem. I didn't put a tree problem on this part, and actually I don't think there's actually a tree problem on the exam. There should be though, right? trust me, you guys will see plenty of trees once we start talking about graph theory. Now, graph theory, I hope that everybody loves graph theory because I think graph theory is pretty freaking cool. Sorry I keep coughing. I swallowed something down the wrong pipe right before the right before the lecture. Okay, so let's look at this thing. So how many times do you have to roll a die before your odds of getting a 1 is greater than 80%? So, okay. This is what we're going to do. So we know that the probability of getting a 1 on a die, if the die is fair, is 1 out of 6. And so the question is, how many times, what is n that we have to roll before we get the odds of getting a 1 are greater than 80%? So if we roll it once, then our odds are going to be 1/6, which is not big enough. If we roll it twice, then it's going to be something around 2/6, right? Not quite, it's actually going to be, if we, 1/6 plus times 5/6 plus, I guess what? The probability of, yeah. Oh no, actually I think it is actually just 2/6 in that case. But anyway, the important fact is that 2/6 is 1/3, so that's not 80%. So let me show you how to do this problem. Let's compute the probability of not getting a 1. After n rolls. And so the probability of not getting a 1, so the probability of not getting a 1 means the probability that we have no successes. X is equal to 0 successes. So really what that means is that that is equal to the probability of a failure to the nth power. So it's going to be 5/6 to the nth power. But we're actually interested in the probability of getting a 1. So we don't want the probability of getting none of the 1s. We want the probability of getting only 1s. So, interesting. So we want the probability of at least 1 success, which is equal to 1 minus 5/6 to the n. And now, here's where the 80% comes in. We want the probability to be bigger than 0.8. So here's how we're going to do this. If the probability of success has to be bigger than 0.8, then basically that's saying that the probability of failure has to be, well, anyway, who cares? Let's just do some algebra. So we do 1 minus 0.8 has to be bigger than 5/6 to the power n. So that means that 0.2 has to be bigger than 5/6 to the power n. Now, here's a question. How do we get n out of this exponent? How do we retrieve n? Yep. So we hit both sides with log. And it doesn't really matter what log you use. You can also use, well, you can't quite use roots, but you can use log. So the log of 0.2 is going to have to be bigger than the n times the log of 5/6. And then all you got to do now is divide. So the only thing to remember is that if you're taking the log of, let's call it tau, and tau is between 0 and 1, then the log of some number between 0 and 1 is actually negative. So when we divide these two things, when we actually say that n, and you notice I'm going to write n is greater than log of 0.2 divided by the log of 5 over 6. And so the reason why I'm saying that it's greater than rather than less than, because remember that n is on this side, is because when you divide by a negative number, it flips the inequality. So this inequality will flip because we have a negative in here. Now, the negative isn't obvious because you see, like log 0.2, there's no negative sign written here. But this is a negative number, that's a negative number. So when we divide by a negative number, when we divide by the log of 5/6, the inequality is going to have to flip. Anyway, let's actually calculate this. So 0.2 log divided by, I guess I could, 5/6 is just 0.83 repeating. So log. And now let's divide the two, and hopefully it doesn't explode. Okay. So n has to be bigger than, I'm seeing 8.82. Now, of course, you can only roll a die a discrete number of times because we're in discrete structures. So you can't roll a die 8.82 times. So really, the number of times that you need to do is 9 times. So to guarantee an 80% chance that you'll see a 1, you need to roll a die 9 times. Isn't that a lot of fun? I think this problem is just one of the coolest problems. Plus, it gives us an excuse to use logs. The way to do it if you're lazy and you don't want to use logs is you can just take 5/6 to the first power, 5/6 to the second power, 5/6 to the 5th power, 6th power, 7th power, 8th power, and be like, ooh, 8th is close, and then do it to the 9th power, and then who doesn't like logs? I would say the vast majority of people hate them, but not us, right? So interesting. All right. So remember that the exam is tomorrow, and if you don't remember that the exam is tomorrow, you'll be reminded that the exam is tomorrow because you will receive an email with the exam. So, all right. Any other questions? Anything else that you want to know before we sign off? And I'll be on the Discord if you have any questions that you want to just ask. So I'll hang around. So it's a PDF. So you submit it like a homework. So the answer is that you can take it. I don't intend for you to finish it in one sitting. I think you should work on a problem or two, take a break, work on a problem or two, take a break, that kind of thing. And eventually, once you're done and you're happy with all of it, you just submit it. That's how it should work. Okay. So you can treat it like a homework. Yes, except I don't want, unlike with homeworks, where I say that it's good to work together on homeworks, I think it's not as good to work together on the exam. I am sorry about that. It's too bad, huh? But that's unfortunately the way it's going to have to be, because it's an exam. All right. I will let you go. Thanks for stopping by. Thanks for sitting through this whole thing. Hopefully this was useful. I think it will be, since I modified some of these problems for the exam problems. Maybe I'll make the exam a little bit easier now that I look at these problems. But anyway, you will see it tomorrow, and it will be whatever it is. All right. I'll see you guys and gals and other people, and maybe aliens watching in the 3rd dimension, 17th dimension. Okay. All right. Bye, everybody.